All right, thanks. I know I am all that stands between you and lunch, so thank you for taking the time to spend with this presentation. So let's see, I'm not sure what each of you think about benchmarks in general and what you think about IoT. You know, you could be a little skeptical, I guess, of benchmarks and what's the intention of a benchmark. I think people have different interests. There's the people who create the benchmarks. There's the people who are providing technology and they want good results for the benchmarks. And then there's the people who are trying to integrate them as well. So there's all different perspectives on them. And I'm going to go through some of these aspects in my talk. So I'm Mark Charlebois. I'm a director of engineering at Qualcomm, and I work in the machine learning group there. So let's see, I am going to go through my agenda here. So in general, I'll just talk about IoT devices, the scale of them, and then what AI on IoT means, in my perspective. Talk about AI on microcontrollers, and then get into some of the benchmarks across the spectrum of IoT devices. Talk about some of the open issues, I think, with regard to benchmarking in this space, and then I'll provide a summary. All right, so I grabbed this off of actually Microsoft site, and it gives you an idea of the spectrum of what we talk about when we say IoT devices. So, you know, we have the Cortex M0, the size of a pinhead, up to these, you know, mobile devices that have 4 gigabytes of RAM in them, tons of computing power, 8 cores, and a spectrum in between. So some of these devices will be CPU only. Some of them will be CPUs plus other accelerators. You'll have GPUs, you'll have DSPs, you'll have NPUs, and so you have a very wide spectrum. So have a look at the size of memory in these things, like 32 kilobytes of memory, right? 800 or 300 kilobytes of memory, 500 megabytes of memory. When I go through this presentation, I'm going to show you some of the models and just try to think of the size of these models based on the size of the memory of these devices. And then we have different categories of devices. So EMBC has, for the benchmarks that they provide, several different categories. Underneath the heterogeneous compute, they have something called MLMark, which I'll talk about for doing machine learning benchmarking. But this just shows that they have to divide things into various classes because there's such a wide range of devices in this space. So there's like ultra low power devices, heterogeneous devices, single core, multi-core, and then the whole phone and tablet class. Okay, so typically when you're going to run a machine learning model on an embedded device in IoT, you're going to take a existing float 32 model. Typically these things have been designed in the cloud and have been running on cloud infrastructure. And then you're going to try to pare that down to something a little smaller. Sometimes you'll prune nodes in the network. But basically you have a Tensorflow model or a PyTorch model, something like that. It could be MXNet. And then once you have that model, you're going to, and it's trained, you're going to go through some sort of conversion or export, typically. And that will use different frameworks, tools to either quantize it, for instance, or change its format and bring it into some internal IR that you can then run inside a runtime. Or you'll do a conversion to a fully compiled model, like the gentleman who just spoke was talking about, and then that would run on the actual device hardware. And could run on a CPU or GPU or an NPU or any combination thereof. So I guess in the last year, TensorFlow can now run on microcontrollers. It's one of the efforts that Google did. And it basically can run on a 16 kilobyte Cortex M3. It has sample projects for things like Arduino, Kel Embed, and they have support across a range of platforms. One of the key use cases is doing hot word detection for like, hey Google, do this type thing. And so there's an overview there of that. But there is another. So ARM&N has a backend for microcontrollers called SimSysNN, and it allows it to run on Cortex-M and actually Cortex-A class devices. And so it provides a library of machine learning functions that lets you run various networks as well. So even this low end of the spectrum can still do AI. Okay, so in the mobile space, the benchmarking is actually pretty mature. So there are a lot of benchmarks already. And these are things that are typically created by a single entity or a single person. And they will take the various frameworks from different providers, and they will integrate them into a single app that can then be downloaded, or variants of the app, that can be then downloaded from the marketplace and then run to create the benchmark. So they would be the ones sort of doing the due diligence about the fairness of the benchmark and the integration. So there's one called AIBench from a guy also nicknamed Ludashi. There's AIBenchmark, which uses the standard Android NN API framework. There's AI22 from N22, NeuralScope, which is a fairly new one, and MLBench. And then there's a couple consortiums that have started up. There's MLPerf, which Google is hosting. And basically, it's free to participate. You can participate on the mailing list. You can join the mailing list. They have typically been focused on server and are now focusing on inferencing that's relevant to mobile devices. And so they're going through all of the requirements and pre-submission stages right now for an upcoming submission. There's some still outstanding issues there. I'm going to go through that in more detail. There's another one out of China, AIIA, which I'll talk about. But typically, these benchmarks, all of them, use either an API, which is a direct Android interface that's standard, or it will use TF Lite, and so they'll bundle TF Lite into the application. Or it will integrate one or more vendor SDKs, like, for instance, the Qualcomm SDK, to let it do acceleration on those particular platforms. And so if I look at the models that are used in this space for mobile, there are typically three kinds of categories. There's object classification, object segmentation, object detection. There's a fairly standard models that are used, like MobileNet, Inception v3, ResNet, DeepLab, and then for object detection, you have SSD variants of the models. This was taken generally from NeuralScope, which had a nice classification, and it gave me the sizes. So when you look at the size now of these networks, you have things that are 102 megabytes, right? Well, that eliminated more than half of the devices that I showed in the initial slide to begin with. So if you quantize those networks, now you're down to about a quarter of the size of them. So now it's more viable to run some of those on a broader range of devices. And so that's why quantized networks, I think, are very important in this space.
So for this quantized version, you use int8,
Yes,
right?
correct.
Okay.
Int8 quantized, yes.
Okay,
Yeah.
okay, great.
They do have gigaflops on there that are used. I don't think they had max per se, but they did say how many gigaflops it was, and I'm not sure if you can translate those exactly. But yeah. Correct. Yeah. And the quantized versions are usually within 1%, but the accuracies are on the site, I believe, there as well. I just didn't want to give you all that information. It's a little bit of overload. Okay, so I'll move on to the EMBC. I'm probably missing an E there. MLMark. So they also, they're a consortium of companies that provides many benchmarks. MLMark is one of them for machine learning. Right now they have 4 targets that, on their website at least, they talk about that they support. There's a Tensorflow Intel there for the OpenVINO, TensorRT, and then ARM-NN on Ubuntu. So you're looking at this class of devices, and you're kind of somewhere in the middle of that spectrum that I showed earlier. There's sort of spotty support, it looks like, for some of these. They only support certain use cases of certain concurrency, but it doesn't really address the whole spectrum of IoT devices either. So the models used, again, very similar: ResNet, MobileNet, MobileNet SSD. One of the other caveats with this, though, is that you have to have a commercial MLMark license in order to, if you're a vendor and you want to publish the results from this. But apparently it doesn't also apply to academic research. So what do they measure in these benchmarks? So there's throughput measurement for frames per second, basically the number of iterations, the number of batch sizes divided by the total time. And then latency, they measure latency for a single interaction. And then they take basically the 95th percentile of that. So sometimes there's a bit of warm-up time. Batch size is 1 for latency. Yeah. And then for accuracy, they measure the top 1 and top 10 for for accuracy. And then for SSD, they do this IOU, which is intersection over union of the mean average precision. So for SSD, you're typically trying to pick out like how many things are there of this particular type in a particular image. And then, just the way floating point results are reported for 3 significant figures. So for MLPerf, it is sort of adapting to this space, getting into what to do with quantized models. They have certain rules that have been evolving. Basically, the system and the framework used have to be available. So it doesn't have to be free and open source, but you have to be able to download it without having a license for it or anything like that. The benchmark implementations have to be shared and open source. So the framework doesn't have to be open source, but how you integrate the framework into the benchmark does need to be open source, and you need to provide that. And so they have certain auditability requirements, and they say that it has to be able to be replicated. You have to have someone follow the steps that you have outlined and actually reproduce your results. So that means that you also must make available the device for which you generated the results. And so if you have like a server behind there and you can create a firewall, that's a great thing. But now if you have a mobile device, you got to have some way to have someone have access to this device, whether they come on site or not. And so these audit rules are actually still under discussion and how they want to implement that. They have 2 scenarios for single stream and multi-stream. So single stream is just basically one stream of inputs that you're processing. Multi-stream would be you have an accelerator back end, and how many concurrent streams can you do simultaneously? There's an open division and a closed division. The open division, the closed division basically says I have very strict rules. You must abide by the rules. You can't retrain the model. You basically have to provide open tools to do any modifications of the model. It has to be within 1% accuracy of the float model, things like that. The open division basically says you can do all kinds of innovative things and then just report your results. And so it's not really an apples to apples comparison. It's more meant to sort of drive the state of the art of benchmarking in a particular category. They provide a load gen framework that basically does the benchmark reporting. And so when you're going to use MLPerf, you have to integrate load gen into your platform and then basically show how you've integrated it. It does a SHA hash of the particular version of load gen that you're using and the code that you used at the time, and then it reports all that back in the benchmark. So the models that it currently has is some for vision, some for language. That's ResNet, MobileNet, and ResNet SSD, MobileNet SSD, and GMNT for language. So they provide typically TensorFlow, sometimes PyTorch models. Sometimes there's quantized models, but it's not an int8 quantized, it's a TensorFlow quantized model. So it's a float model that's been built with quantization awareness. And then you can use tools to actually quantize that to an 8-bit network. But they say that if you're going to report the results, that if it's a quantized network, it has to be within 1% of the accuracy of the floating point model. Okay, there's another alliance. This one is out of China, and it's the Artificial Intelligence Industry Alliance. It's called AIBench, and it supports multiple frameworks. So there's a Snappy, High AI, T-Engine, and TF-Lite. And so this is similar to the other mobile benchmarks I showed before, where you have an app that basically integrates a bunch of vendor SDKs and then can run these frameworks. And so you have sort of these 2 models, right? You have one where I want to run this benchmark, and I have to integrate their framework and then report the results. And then you have another where I provide you with my SDK, and somebody bundles all these SDK together and then creates an app and then says, well, I know I've done this in a fair way, so I can represent that these results are fair. Otherwise, you have to have some auditability if I'm self-reporting the results, that what I've done is actually reproducible and accurate. So for object detection, they're using here MobileNet, MobileNet v2, and VGG. So I'm just going to point out VGG. VGG is a massive network of, it's 528 megabytes. And so even for mobile devices, that can be actually quite a large network. And they use a couple different ones. They have a VDSR case, which is basically for, it's a, what is that? I can't remember the acronym, but it's basically used for taking an image and upscaling it to a much larger image. Super resolution, basically. And then FCN was a different one from Deep Lab that was used for image segmentation. For time. All right, open issues. So there's lots of open issues with regard to benchmarking in IoT. In order to run these networks that are meant to be run on servers that are now kind of capable of running on mobile devices to now run on much, much smaller devices, there's a lot of active research going on to try to shrink these models as much as they can, how to prune them, how to retrain them, how to quantize them, and keep good accuracy. And so it's really hard to do an apples-to-apples comparison across platforms when you're using different approaches to pruning and changing these models. At what point are the models not the same anymore? And at which point are you just actually testing a use case as opposed to a particular model? And so the other part is if someone else isn't doing the integration of a particular runtime and running a particular model on those runtimes without retraining, how do you then verify the accuracy and reproducibility of those results? And so you need to have some sort of openness when you're doing this so that there is something like MLPerf is describing where if you're going to self-report, there's some sort of auditability or way for someone to validate your results. Quantized models versus floating point models. Floating point seems to be, again, the old standard. I think in IoT, quantized models are going to be very important. And then the runtimes versus compiled models. Testing on things like Android, where you have a standardized interface, is certainly one class of tests. If you have runtimes and you're testing a particular model that you're deploying across runtimes, that's another case. But if you're compiling a model and you're changing it and you're optimizing it and you're specializing it, at which point is that too much change for you to actually have an apples-to-apples comparison? And you need some rules around that. And then what do we want to measure? Like, typically people like to throw TOPS around, right? Trillions of operations per second. But is that the most interesting measure, right? If your thing takes like 300 watts, is that really that interesting? Maybe TOPS per watt is more interesting. Or maybe TOPS per dollar, if really what you care about is the BOM cost of your device. Or the size, depending on if you're integrating the IP. But TOPS really doesn't matter if the thing doesn't run your model. You can have tons of max that the thing can do, but if it doesn't actually support the ops that you need to run your model, it's not going to run in the time and the KPIs that you need. So maybe what's more important is the FPS per watt, right? The number of frames per second you can actually process for a particular model per watt. And then accuracy. Is accuracy the most important thing? But then there's trade-offs for accuracy and speed. At which point is the accuracy good enough for the use case at a particular frame rate? And then power. How do you measure power? Is it the power of the accelerator? Is it the power of the platform? What else is going on in the platform at the same time? How do you control all those variables? And then, and clearly the current models that are used in the mobile benchmarks are just really not applicable to a vast majority of the kinds of devices in the spectrum of IoT devices. Yeah, so I've covered a lot of that already about what is allowed. Do you allow retraining? If you are doing retraining, are you really testing the same thing? Are you just testing a use case? And maybe that's what you want to do, is test, how good can I solve this use case on this device versus how good can I run this model on this device? The models have typically been PyTorch models or TensorFlow models for this. What about ONNX models? If we have a lot of runtimes that support ONNX, should some of these models be supported and provided in the ONNX format? What are the use cases that are important for IoT? Is it object detection, face detection, hardware detection? And then, yeah. So again, there are some of these benchmarks like for mobile, like Ludashi, for instance. And the way they work is they have a bunch of models that they run. They do have some sort of bias weighting for accuracy of the particular model, but then they score and weight the different models differently. And so they come up with some aggregate score for all these things, but there may be an implied bias in there about which models are weighted more heavily, which ones favor one particular approach versus another. And so it's very hard to come up with a fair measure using this kind of aggregate score approach. And so what do you do for the trade-offs for accuracy and speed? And the current approach also sort of overlooks a fundamental part of these IoT devices, right? Which is the concurrent capabilities of the device. What can it do for preprocessing? How many concurrent pieces of IP are there that do AI? Are there multiple DSPs and a GPU and a CPU that could all be doing different AI jobs at the same time? Is it the aggregate capabilities of the device that's actually important? If I have something that needs to run 3 concurrent networks and they need to run reliably and deterministically, maybe I run them on different IP blocks and I can do that use case, and that's actually what I need for my particular product. So in summary, the existing benchmarks don't really address the whole range of IoT devices that are there today that do AI. The types of models that we should probably consider for AI probably vary across the classes of IoT devices, and we really should think about what's most relevant for those classes. Quantized models, clearly for size, are going to be very important in this space. And tools that allow you to run quantized models while keeping accuracy are also going to be very important. TOPS per watt or frames per second per watt are probably way more relevant than TOPS by itself in most cases. And when we're looking at benchmarks and we're looking at customization, if you're going to run a benchmark of a model, there's a point at which too much customization really doesn't give you a fair comparison or a meaningful comparison. And then in the end, what is it that we want to say about IoT devices? Is it how fast it can run a particular model? Or is it what are the capabilities of a particular IoT device? All right, that's the end of my talk. Happy to answer any questions anybody has. Yes?
So at the end of the day, I mean, first of all, before I came to NXP, I ran Embassy for 20 years. So
Okay.
as I was leaving, it was still working on the MLMark thing. And so, on the other side of the fence here now, you come to realize that the competitive benchmarking environment is not really the key thing because there's so many ways that you can play games there. And really what ends up happening is customer comes to you and says, hey, I need you to run faster RCNN in 8 frames per second. Can you do it?
Yeah.
And end of story, right? So we have to ask the philosophical question. I mean, and maybe that's part of what you're thinking about here too, as well as, do I really need to play these games that these entities are deriving? I mean, what's your thought on that?
Yeah, well, yeah. So I think it depends where it's coming from, right? If you have a benchmark vendor who has set a mark to beat, to say, here's my constraints and here's the use case, and now you have to sort of contort yourself to fit my use case, then you're doing something for the sake of the benchmark, which is not necessarily what a customer cares about. But it depends, in your market segment. Sometimes why people buy certain devices is because of benchmarks, and you have to be real about that too.
Yeah, and what's really cool about the space of ML though is the benchmarks that we're running are real more or less applications, right? Except, you know, you don't have any pre-processing in there and all that kind of front-end stuff. But, you know, everybody's doing a mobile net or a ResNet or a YOLO, and maybe they do make some optimizations in the final application. But I don't know. It's a different feeling for me here, where we don't need to play benchmarking games, right? We can just go get these real workloads that are available, as opposed to something like CoreMark, which is synthetic, and Spec, which is synthetic, and all that, right?
Sure, but then what do you use as a basis for comparison? If you're saying for a particular model on this particular device, I can run it at so many frames per second, or I can do it at so many frames per second per watt if I really actually care about power. Maybe that's more interesting.
Yeah. We could talk about this for a while.
Great, thank you very much.